Hey, so welcome back, and this is another daily code problem. So today it's called Partition Equal Subset Sum. And so you're just getting an array here called nums. And essentially you're just going to return a Boolean if you can kind of split this array into two different sets that the sum of them is equal to the same thing. And so what that's going to look like is, say if we're given this array here, you can split it into 1, 5, 5 as one set, and then another set where it's just 11. And if you take the sum of these two sets, so these add up to 11, and well, 11 of course is just itself, so that's 11. You can see that these actually have the same sum. And so in this case, we're going to return true, because we were able to divide this single set into two, that both, when you take the sum, they're equal to each other. Okay, but if you're given this one here, you're not actually able to split it into two sets such that they're able to be equal to each other when you sum them all up. So you just say false. Okay, so if we kind of think about the recursive relationship that we see when we are trying to compute this, you might come up with something like, okay, we're given 1, 5, 11, 5. And so you can start maybe from left to right here, so from index 0 onwards to the final index. And so when you look at 1, you can kind of decide whether you want to add it to the first set or to the second set. So this is kind of set 1, which is empty. Maybe you want to add it to the second set, so you make it like this. Or you could decide that you could add it to the first set, like so. All right, and then the other one would be empty. And so when you move on to the next decision, you can decide where you want to put 5. And so then 5 could either be on the left side here, and so then it's and 1 on the right, or you could decide to go down a different path where it's still empty on this side, but then the other set is now 1, 5. Okay, and so you can then imagine that the same thing would happen with this, where you have two choices, where you could either put 5 on this set or the other one. Okay, but you might be able to see that there's a lot of repeated work going on, so we're going to use memoization, which is a common approach for caching or just making sure that we don't do a lot of repeated work. And so this is basically what I'm going to do is the top-down memoization solution. Now you might try it, and kind of the approach that I outlined there will get a memory limit exceeded. And you can kind of see it here where this is the two different possible paths, and we just want to see if either of these paths return true, then we propagate that answer up. And so this recursive relationship, we're just keeping track of essentially a pointer that we're moving across, and then the left sum and the right sum. But the problem is as we're caching this, basically the keys that you're using for that cache lookup is just like too verbose, and there's just too many possible results that we're storing here, so we're going to get that memory limit exceeded. But you can actually do kind of a special way, so you can kind of limit the search space that you're using when you're storing that cache. And so what that's going to look like is actually you can just look at, and when we're defining this, our DP array, we're going to still have the index, but we're just going to return or store one particular sum here. And so what that kind of means is essentially a good edge case that you can check here is basically, okay, is nums divided by 2 equal to nums rounded down division by 2? And this basically just checks, okay, can we even split this in half? Because when you're given these sums, if they were to equal each other, you must be able to kind of split them logically in half. Otherwise, you'll never be able to find two sets that will equal each other. And so if these don't equal the same thing, you can just return false immediately here. And the reason why this kind of relates to what I'm talking about here is essentially we just need to find some amount that is equal to like 1/2 of the total sum. Sorry, this is supposed to be the total sum, so I'll just write that as total. And so total will be equal to the sum of all these numbers, yeah. And so if the total sums don't equal each other, when you round down or like an integer division, then you just say return false. And so we're just trying to find some amount that is equal to the kind of division of 2 or 1/2 of the total sum. All right, and so we're basically going to return dp of 0, 0 for this point, like so, and we want to cache this, of course. And so from here, basically, we need to find this. And so naturally, we're going to want a base case. And so the first thing you typically want to do is just check, okay, is our I equal to or kind of out of bounds? And so we just check the length. But then we're also going to want to check the bounds on this kind of total amount that we're trying to obtain. And so if the amount is also, or otherwise, if the amount is greater than or equal to that kind of 1/2 point, then let's just check, okay, have we reached that goal, which is essentially exactly 1/2 of the total amount. So this is an amount here, this should be, or yeah, no, that's good. So if the amount is equal to the total amount, then we would return true. All right, and so that's basically the base case. But in order to get there, we want to have some recursive relationship that we're creating. And so we're basically going to return 2 possible paths, which is, okay, naturally we're going to want to increment our DP array by 1 for each of these paths. But the way they differ is one path you're actually going to include the current number at this point, or we can just exclude it and just kind of continue the current number. And so that's just a way so that you kind of pick and choose which numbers we add to the current sum, because we're really just trying to find some pair of numbers that is equal to 1/2 of the total amount. All right, and so let's go ahead and run that. Looks good. Oh, index out of bounds, so why is that? If it's greater than that, nums at I, so that's index out of range. Oh, this should be an or, sorry. Yeah, because otherwise we want to check both of these individually. And success. So yeah, I hope that helped, and good luck with the rest of your algorithms. Thanks for watching.